And I would not be surprised if someone is trying to reenact all the experiments in the bathroom.
Some of them belong there. Getting blown off the toilet seat.
All right, so the current homework assignment is due, and we are going to work on the next one, but you already know what the next one is because we have been talking about it for some time already. Okay, so let me just go to the homework assignment. Okay, so this is where we are. We are now talking about, we are in socket programming, and the homework assignment that was due today was the first one, which is socket programming, and the new homework assignment is socket 2. It is a single-threaded, multiple-client program. So we'll take a look at this program and make sure that we update the due date so that you know when it is going to be due. So we just have to change the year. And the time is right, and 1 week from today is going to be the 26th. 26th of March, 2012. So everything else can be kept the same. And we'll go ahead and go over the homework assignment because now it is your active homework assignment. All right. We talked about the makefile last time already. I'm pretty sure I talked about it. It is up to you guys to decide how grandiose you want to make your makefile. You can make it really complicated. You can make it complicated but flexible. In other words, it's not only for this class, you can also make it so that it is easy to use the same makefile for your own projects and for your other classes. Or you can make a file that is very simple, but it will only be useful for this particular homework assignment. So I will leave that up to you guys. I do not impose any particular structure regarding how you organize your source files. If you want to put everything into the same source file, that's fine with me. If you want to put everything into the main function, that's fine with me too, because I'm not the one who is writing the program. I'm the one who will be creating the program, not writing the program. I do read your code, okay, just so that you know that I do read your code, and that's why when I graded MBR Viewer last night, there were a few surprises, let's just say, okay? Because in that homework assignment, you're supposed to read from standard in, okay? So let me just kind of go back to the homework assignment, talk about it first, because I think it is important that everybody will read the specification first and make sure that it is all conforming to that standard. Otherwise, my program it's really hard to grade it. This is the MBR reader program. So as far as input is concerned, you may assume the input is redirected from the command line. Okay, so that means you should be reading standard in and not be reading mbr.bin. Okay, and my test script was set up based on this assumption. So when I test programs, I was using less than and then the file name that will be serving as your test test code. And of course, some programs, did not work because, it wasn't, reading from standard in. It was trying to open mbr.bin and read from that file. If I did not read the source code of your programs, I would have given those, people like a really, really low score, if any, because it just didn't work. So when I read the code, I realized, oh, okay, so that's why the program is not working. It's because it is reading from mbr.bin instead of standard in. So I had to change my test script to accommodate that. And then as I tested and tested, one program did not work again. Okay, and then when I read the source file, that program was using the command line to specify the file to read in. It was using argv_1 to specify the name of the MBR file. So once again, I had to go back and change my script again to accommodate for that. I could have just graded it, just one homework assignment by hand and not use the script, but I just felt that I should make my script accommodate all the different cases. So anyway, I spent last night pretty much grading this homework assignment, rewriting my test script as I encounter programs that do not conform to this standard. Okay. So are there any questions at this point about the homework assignment? This particular one was graded. If you turn in late, turn it in by email for one reason or another, just remind me so that I can go back and look for your submission by email. Because I was only grading by Moodle last night, I did not use my email for that purpose yesterday. All right, so that's out of the way. Now we can go back and continue to talk about this one. All right, so use a makefile. The makefile should have a clean target to delete all object and executable files. We talked about this last time already, so I don't think, I actually gave you an entire complete, makefile, so I don't think, we have any questions left regarding the makefile. Okay, do you guys still remember last time? I actually, in fact, I can go back to the notes from last time, 2012, 03, 14. So, it's done, really. This is not a very good makefile because it is very brittle, okay? This is very brittle in the sense that if you want to use multiple source files to handle your project, you have to make changes to a few lines, not just one. If you make changes to only one line, the program, or the makefile does not work. You have to make consistent changes to multiple lines in order for this approach to work. I also showed you last time, the general notes on makefiles. So let me go to that note here. Just look for makefile, and here we have, how to create a makefile as a link. So you're more than welcome to read that. It's not, like, a single page of quick reading, but I think if you plan to become a developer who will have to deal with C++, C or Java programs, this would not be a bad idea. It's not a bad idea to get to know the make utility program because it truly is a useful tool. It's not only useful for compiling programs, it's also useful for just about anything that has a dependency structure to it. You can use the make program to automatically test your code. Whenever you write some code, you can do regression test using the make file. You have to learn a little bit more how to structure your code and how to separate the files and how to use symlinks, but you can do it with make. So this is a very useful tool. I strongly recommend everybody to try to learn as much as you can of how to use the make file.
Did you know there's a typo in 4.3 on there?
4.3?
So you have the fourth line down, you have SRC, but towards the very end, I think you have
CSRC for C source. Yep. Ah, okay, we can change that. I wrote this. I changed it a few times. The first time I wrote it, it was only for one single type of source files, and then changed it to multiple types of source files. And that's why it has different versions. Yep.
You also set LD flags, but you never use it, and I thought you had to export it if you wanted it to be visible to others.
These are special because these flags are internally used by make. So it gets passed on. You use GCC to do compiling, but you also use GCC to link. When you specify LD flags, it means it only applies when it's linking, but not when it is compiling. When it's compiling, it uses CXX flags. So in this case, I turn off optimization because I didn't specify a number. Turn on all the warnings and also turn on debugging.
But you actually use CXX flags in your, at least in your comments. You list GCC CXX flags, and yet you never use LD flags.
It's actually never used because these were commented out.
Right.
So the files that it actually relies on in order to do the compilation are coming from the .d files, and the .d files do not specify the command to compile. It just lists the dependency. The command to do it is implicit. It is built into the make utility program. Basically, every time you use make, it has an implicit pound include, if you will, including a standard tool list. So it knows when it sees a certain extension, it knows how to convert that to a target of a particular extension. All right. But this will be a pretty easy fix, for people who want to fix this one. Just change SRC to use CSRC consistently. So either change this one to a single SRC or change the other ones to CSRC. All right. Any other questions? No questions? Okay, so here's the description of what your next program is supposed to do. From the server side perspective, what you need to do is you have to wait until all 3 clients connect. So the first thing you want to do is to sit in a loop to accept connections from exactly 3 clients. So don't start the rest of the program until you have 3 clients talking to you from the server perspective. The server does not send the circle is complete message. So that part is not gonna is not needed or wanted in this particular program. It's going to be a silent accept. You cannot see, or it doesn't send any message to the clients. If you want to print out some debug messages to confirm that yes I did get one client, you can do so by sending it to standard out on the client on the server side. Instead, the server should do the following. So what it needs to do is to listen to all 3 client connections. If any client has anything to send to you, you need to broadcast that to all the other clients. Keep track of which client is still active. If a client is closed, do not use it anymore. Okay? And when all 3 clients' connections are closed, then at that point you can close the endpoint socket, unlink the socket file created, and exit. Are we doing okay so far with the behavior of this program? The client side, or each client, should do the following. Instead of just listening to the connection and echoing to standard out, which is what you did in the current homework assignment. So what you want to do is to echo everything from standard in to the socket connection, and then you want to echo everything from the socket connection to standard out. Are we doing okay so far with this? Okay. When standard in closes, which means when you press Ctrl D on the keyboard and press the Enter key, then you can close standard in. Then you also want the client to close the connection and then exit. Even if the server still has stuff to send you, you just close the connection and say, okay, I'm done here, I'm quitting. All connections should be set up to be blocking. In other words, do not set up the connections to be non-blocking. I haven't taught you guys how to set it up to be non-blocking. So if you use just open, socket, and all the other calls that we have talked about, the way we have talked about, they will all be blocking. They're not non-blocking. To accomplish this, you will need to use the system called call select. I demonstrated how to use the select call in the previous class. Okay, so you pretty much want to use the select call. Use man to select to read the manual page of this system call. To simplify matters a little bit, you don't need to use the timeout feature because this is going to be your next homework assignment. Socket 4, this is socket 2, so socket 3 is going to utilize a timeout feature. Okay. Note that the man page includes a simple example to illustrate how to use the select call for a very simple task. You might want to read that first, okay? Because it's a sample program, it is documented. Let me just switch back to the man page so that you can see what I'm talking about. Okay, if you just go all the way to the end, there's a sample program right here. And it is also commented. Now this one does make use of the timeout feature, so you can just ignore that part. In other words, when you call select, turn this one into a null as well. If that is a null pointer, that means it is not going to time out anything. All right, but this is a very simple program, and use it to help you understand how to use a select call. Any questions at this point? Yes.
When you were saying about, can you go back to the assignment?
Yep.
Where we were talking about when STDN closes, closes the connection and exit. So is that when the basically coming from the server, right?
Yep. Okay. Let me do it this way. Okay. In order to demonstrate what your program is supposed to do, I'm going to use a technique called a gosh, I cannot remember the name of it. This is borrowed from the UML, the Unified Modeling Language. It's a scenario. I think it's called a scenario graph or scenario picture. But anyway, you will see what I mean by that. Okay, I'm going to use a spreadsheet for that purpose. Okay, so what this picture is going to do, or what this spreadsheet is going to do, is it will have all the different parties involved in this particular homework assignment. So we have a server, we have client 1, client 2, and then we have client 3. I will shrink the columns so that we can see everything a little bit more easily. It does not shrink the empty columns. It's so odd. Okay, there we go. So when you look at this picture, each row is a time slice, is a slice in time, and when you look at a column, those are the activities or things that happen for that particular machine or that particular program in this case. So what the server needs to do first is, you already know this part. You use the socket call to create a socket endpoint. You use the bind call to bind the socket to a named socket. And then you can use the listen call to say that we are open for business. So these three things are for the initialization on the server side. You only have to do it once. And then after that, the server will run accept. Let's say client 1, okay, what client 1 needs to do at the same time or later. Okay, you don't want to run client 1 until the server is up and running, because otherwise it will not be able to make the connection. So let's say we run client 1 after server, the server is at least at the point of accept. Client 1 first has to run socket or call socket to create the socket endpoint, and then it has to call connect in order to talk to the client. And then the client, talk to the server. The server at this point will accept that call, and then it will go back to accept again. And then socket client 2 will do the same thing. Does everybody understand how this picture works? Okay, it's just a, if you will, it's really just a play, a script for all the different actors in this particular scenario. Are we doing okay so far? Okay, so at this point, we have all three connections accepted. So we have three active connections. So the server at this point will go, it will use the select call and go to sleep. In other words, it's saying, well, I'm not going to do anything here. There's nothing for me to do. I'm waiting for at least one of the clients to talk to me first. There's nothing that I'm going to do actively. Is that okay? Client 1 will also do a select call. Client 2 will do a select call. And client 3 would also do a select call. The main difference between the select call from the client's perspective and the select call on the server side is the clients have to select on a few things. Each client has to select on the two possible ways of input. One is to read from the socket file descriptor, and the other one is to read from standard in. The server on the other side, on the other hand, will only have to listen from the sockets. Okay? Because that part is very important, okay? Because you have to set up the select calls correctly, otherwise your program will never unblock correctly and continue execution. So let's say client 1, gets something from its standard in, okay? So we'll just say, we have a character of A from standard in. Okay? Because you're typing, a character on the keyboard and then you press the enter key, that will unblock select. After select returns, you have to scan using FD is set, okay, in a loop to scan and see which file descriptor has something to read from, and then you will find that as standard in this case, or file descriptor 0, has a character, at least one character to read. Read that one single character. When the client is done reading that one single character, then it will do another select call to wait on write. Okay, because you're not guaranteed that the write will always happen. Now this part is kind of optional because you're handling, byte by byte, so, and you don't really have a buffer. So if you prefer not to select here, you can just go ahead and write A to the socket. Okay, because the select is not really going to buy you anything. You cannot continue to go back and try to read another character from standard in until this byte is written to the server, because you are not going to implement your own buffer. Okay, for those of you who want to overachieve, just kind of refrain from overachieving this time and not implement your buffer. We only need to read and write one byte at a time. Okay, so this one will write A to the server. So what will happen here is the server is going to unblock its select. So the server will read A from that particular socket, one of the sockets from client one. So let me just make this more clear. Okay. And then what the server will do at this point is to broadcast this character to all three clients. Okay. So now the server will have to say select on write all clients. And I know this is going to be a problem, so what we'll do is to change the alignment and use auto wrap here. And also change this so that we can scroll while retaining a portion of the screen, top part. Are we doing okay so far with this one here? Yep.
Yeah, the select, I'm confused. Why aren't you just using a write call and writing to all of your clients?
Because you don't know who is ready to accept your writing. Because one particular client can be sleeping and not wanting to read from your socket, not read from the server. So you don't want to write to that one first because it's going to block everything. You want to write to the clients who are ready to write to, and the one that you have to wait, you only wait when you have to. Okay, let me just re-explain this part here. Okay, so let's say you are the first client who sent me a byte. So I receive your byte. I got your byte here, and then I say, okay, here's the content, the lowercase a character that I have to broadcast to all the clients. So let's say the three students in the front row here are my clients. Okay, so I'm going to say, okay, I have to broadcast or send this character to each and every single one of you. Okay, that's what I need to do. But I don't know which one of you is ready to receive the letter yet. Okay, so that's why I need to use a select call on write on those three particular file descriptors, but on write operations, because I'm not reading anymore. I have to handle this byte first before my hand is available to hold another character, because I'm only buffering by one single character in this case. So instead of always writing to you first, I'm going to say, okay, whichever one of you is ready to receive this byte, let me know. And that's the job of the select call. The select call will unblock as soon as one of you is ready to receive this byte, or all of you at the same time sometimes. Okay, I don't know what the scenario is going to be, but it will only unblock if at least one of you is ready. So let's just say that of all the three clients, maybe two clients are doing something, or maybe they're blocked for some reason or another, and you are the only one that is available to read from. The select call is going to unblock, and from scanning using fd underscore is set, I can detect that the file descriptor corresponding to you I can write to. So what I will, as a server, what I do is, okay, here's your byte. Okay, I write to your socket, and then I'll be done. So you have to do your own thing to receive that byte and echo it back onto your own standard byte. But that's your job. I don't care. Okay, once I write a byte to you, I'm done. But the server still has to keep track of, okay, who else still need this byte? Because because I'm supposed to broadcast the same byte to all 3 clients before I move on. So the next select call, I have to block on only the 2 remaining clients. I don't have to put you on the select call anymore because you have this byte already. So I don't really need to wait for you to be able to receive another byte. I just need to select on you 2. Okay? So let's say you are the next one who's available. So then I will just say, okay, the select call from the server side will unblock, and then I will say, I will scan through it, find out that your file descriptor is unblocked on write. Then I'll just write this single byte to you, and then I will wait on the last client in that case. So if the last client decides to kind of, decides that that process or that client is not ready to receive the byte, then I cannot do anything else. I have to block. At that time, I can, even if both of you have bytes to send to me because your standard in has stuff, I cannot receive your byte yet because I have to handle this byte first. Are we doing okay so far?
So you're resetting up your select call each time. Is that true?
Correct.
So you're
Every
figuring
time
out
you
what
select.
you're doing what you need to do, and then you're
Right.
resetting up your select call, knowing I've taken care of that client, so now my select call is going to look different. I just need to wait for those.
Correct.
And you write to her, and then you say, okay, now I just have this guy left,
Yep.
and I redo my select call.
Yep. In other words, the server has to keep track of the state of the broadcast process. Am I done with broadcasting to all clients? If not, I want to check who has not received this byte yet and do a select on write for those particular clients. When I'm done writing to everybody, then I know I can change my state back to, okay, I'll receive a byte from the 3 clients. Are we doing okay so far with this explanation? Okay, so I'll try my best to write it here. Select on call for all 3 clients. So let's say this one is ready first. Okay. So then I will write to client 2. Client 2's own select call will unblock. So client 2 will first do a read from the socket, and then write to standard out, and then back to read again. Okay? But you don't just read, you basically have to do a select in this case. Because you don't know from the client perspective, you don't know which file descriptor will be ready first. Is it going to be your standard in that will give you a byte first, or is it the socket that will give you a byte first? You don't know, because one is controlled by the server and also the other clients, whether they have something to broadcast, and the other one is controlled by the end user, typing something on the keyboard. And because you cannot really tell which one will have something to go first, you have to use a select call so that you can unblock on either one of those particular file descriptors. Are we doing okay so far with this? Yep.
So client 2 at this point is running a select call for read from either the socket or the read from the socket or from the mouse.
Right. So when the server has to select again, it doesn't have to select for all 3 clients anymore. This time it will only be client 1 and client 3 because client 2 is already got that byte. Okay. So let's say after this, client 1 is the one that says, okay, I have a byte available. So in that case, this will unblock. Then you'll write to say client 1. Client 1 will read that byte. It will echo it to standard out, and then it will go back to its own select. Okay, read from socket. Are we doing okay so far with this picture? Remember now, this is called a use case diagram in the unified modeling language. Okay, so once client 1 reads, okay, I'll just use it this way. So once the server is done writing to client 1 and client 2, then it only has one single client that has not received that byte yet. So the third time you select on the server side, then you only have to write to client 3. because that's the only client who has not received that byte yet. Okay? But this also means that if client 3 is not ready to receive a byte, it's going to block the entire thing. There's no way around it. Yep.
On your left column, you say write to client 1, and then in the client 1 column it says read from socket. There's really no delay time between write to client 1 and select on write to client 3, right?
You mean from here to here?
Yeah, you see the empty, the number 24 is empty right there?
But they don't happen at the same time either. Because this event has to happen before this event can happen.
But I hear what you're saying,
There's a latency, but not but not a block. Yes.
Right, because the server is just doing his business and moving on, right?
Correct. That is correct. So so this is only representing the ordering of events. It has to be ordered like this. The server has to write to client 1 first, and then the client 1 will basically return from the select call and read from that socket. Yep.
But technically, couldn't the server select on write client 3 at essentially the same time that client 1 is reading from that socket?
Makes sense.
I think what they're saying is can you delete A24?
You mean to move this one up?
Yeah.
Yeah, you can. Yep. Yep. So if you want to, this can happen. All right. So as soon as client 1 reads from that socket, well, we don't even care, because when it reads from the socket, it's not the business of the server. So the server can immediately select on write to client 3, and then when client 3 says I'm ready to receive a byte, then it will return from the select call, then we can write to client 3, and then client 3 will unblock from its own select, and it will do a read from the socket. It will do a write to standard out, and it will go back to the select call again. So if I want to be complete, it would be read from socket. Okay. The same typo. Write to standard out. And that completes the first. That completes one basic cycle. Okay. So the basic cycle starts from row 18, reading a byte, unblocking from a select. Okay. So let me just finish the whole thing. So this will be select from on read from all clients, and it's the same thing as this one here. There we go. Yep.
Dr. Tack, what did you call that again? A use case in unified modeling? What did you call it?
Yeah, it's called a use case diagram.
Use case diagram. Thank you.
So if you go to search for that, it's called a use case diagram. Nope, I was wrong. It's not a use case diagram. It's a scenario. The use case diagram is something different. I'm sorry, I got it wrong. Scenario. Yep, there you go. Yep.
Okay, scenario diagram.
Yes. There we go. This is a better picture. It's basically using one column per agent. An agent can be an end user, can be a program that is reactive, and so on and so forth.
Right.
And then you use the vertical axis for time, and then you use horizontal lines to represent interaction. Who is talking to whom, sending what message, doing what. And that way, it's basically a crude way of doing a script, if you will, for a play that involves all the different agents in an information system. And of course, I was really lazy and not use the arrows, but in this case, the arrows can be implied pretty easily. Yep.
So I think that also one of my questions is at what point, or what are we checking for to know if a client disconnects? Is there? I know that if the if a file descriptor closes, then it basically sends an end of file
Yes.
character. Is that the only thing we're looking for?
That's the only thing you can look for. Okay, let me continue with this scenario diagram to handle that. Okay, so let's just say that client to okay, this select is select on read of standard in. So let's say here standard in and count end of file. Okay. Now that is detectable only by unblocking the select call. In other words, if you're selecting on read for your standard in, and the end user presses Control D and then press the Enter key, the select call unblocks, which means you will have to scan for which file descriptor has something to read, and your scan will indicate that standard in has something to read. Even though it is end of file, it will still say that, hey, I got something here. It's basically an event. It is not something that you can read, but there's an event you should try to read. But when you read, it will report back and say, oh, you just read 0 bytes, which is the condition that you use to detect end of file.
Yeah.
Okay? So when standard in sees end of file on client 2, then client 2 doesn't have to do anything. Okay, client 2 simply exits. Okay, well, if you prefer, want to close. Yep.
Does read return -1? I thought that was what happens when you get to end of file.
No, read returns 0 when you encounter end of file.
Oh, it returns 0.
It returns a 0.
-1. When does it return -1?
I do not think so. I think -1 is an error condition. Okay, when you look at return value, on success, the number of bytes read is returned. 0 indicates end of file. So 0 is not a error condition. It is simply end of file. On error, on the other hand, 0 is returned. But your program doesn't have to handle errors. It just has to handle end of file. All right. So when client 2 unblocks from select, it will do a read. When it reads, it will read back 0 bytes. Read itself returns 0. When that happens, you have to close all the file descriptors. Be a nice program, clean up after yourself, and there's nothing to do. Okay, so it will exit. Now, when you close all the file descriptors, that will also include the file descriptor of the socket to the server. So when you close that socket from the client side, the server will see the same thing. It will unblock the select on read on the server side. Okay, so the server side will unblock on select, and then the server will try to read from, in this case, client 2, because the flags, or not the flags, but the file descriptor set of the server will indicate, hey, the socket corresponding to client 2 has something ready. Okay, there's an event. Okay, there's an event. You should take care of it. So as you try to read from client 2, you will read back, hey, this is just end of file. Okay, so you will basically detect end of file at this point, and then what you need to do is to remove client 2 from all further activities. In other words, you do not listen from client 2 anymore. You don't broadcast to client 2 anymore. Client 2 is gone.
So you're going to read and you're going to get the 0 again. You're going to get 0 bytes.
I do not know, if you repeatedly read what you're going to read back. If you read once, definitely you will read back a value of 0.
I think I remember the man page, maybe for read, specifically saying, do not try to read again. I think it may be an undefined behavior.
Okay, very good. So are we okay with this picture? So when this happens to all 3 clients, when you detect end of file of all of the socket for each client, and you have no clients left, then the server can exit at that point, because there's no one to listen to and no one to broadcast to, and it's time to exit. Are we doing okay so far with this homework assignment? Okay. So I think this is a good picture. So we'll go ahead and save it and call it the scenario diagram. So my recommendation is to use a structure to represent each client. Because not only do you have to keep track of the file descriptors for the socket, you also have to keep track of the state of the client. Have I broadcasted to this client already? Well, you kind of have to remember that. Now, one little trick you can do if you don't want to use this approach is you can use FDset to kind of remember, which client still needs to be broadcasted to. But that's really not a very good idea. You should have one flag in the data structure for each client to represent, have I broadcasted to this client? If you have not, then you want to put the select on write for that particular client on into the write file descriptor set. If the client has been broadcasted already, you have already broadcasted a particular character, you want to remember that because you don't want to broadcast the same character again to this client. Are there any questions? There's also no need to overachieve and try to make sure that the attempt to read from the clients would be fair. Okay, let me explain what I mean by that, because some of you will think about this and then say, okay, do we need to have to enforce a round robin method so that each client gets its turn to talk when you have a particularly talkative client who wants to hog the broadcast method? Okay, so let's say that we have the same 3 clients, okay, 1, 2, and 3. You have a byte to send to me, okay, I receive a byte and broadcast to all 3. Okay, then I have to go back and try to listen to all 3 clients again once I broadcast the previous character. The question is, if multiple clients are ready to send something to me, because I can see that from my select call, okay, who has something to send to me. So let's say all 3 of you have something to send to me. Who should I read from? Yep.
It is really, really important if you're reading byte by byte that you read from the same client until his message is done, or all of the messages are going to be completely garbled.
Well, but since we don't have a defined protocol, each message, each packet is really just 1 byte. Because what you said is true. If you have a protocol already defined and say that this string has to be sent without any interleave, right? Okay. But since we don't have a protocol defined, it doesn't really matter. It's just byte by byte. But but I still have a question of who am I going to listen to next?
It should be one of them.
Well, the homework description does not specify whether it has to be fair, because I can just be lazy. Okay, from the programming perspective, it is easier just to use a loop. Okay, to loop through all the clients and see who has something to talk to me. So I'm going to always start with you. So if you always have something to send to me, the other 2 will never get a chance to send that something. So they will still be receiving the broadcast all day long. Their standard out will be filled with your stuff. But they will never get a chance to send a byte to the server so I can broadcast their content to you. Okay. So in this case, because the behavior is not specified, you can go with a lazy way and just use a particular priority level, a fixed priority level, instead of trying to maintain a round robin method. A round robin method means I have talked to you already. If you're the only one with something to send to me, I will take your byte. Okay, it's not a problem. But if other people also have something to talk to me, I'll just say, okay, I talked to you last time already. This is somebody else's turn, and then after that, if only one of you have something to say, I still have to listen to you. But if all 3 have something to send to me, then I have to accept his connection first.
You can still do a round robin and a loop though. Because
But
you
you
can do
can't
your
really-
select and then you deal with everybody who has something to say to you. And then you go back to your select call.
But it won't work because sometimes they don't have anything to say.
Right, but your select said somebody had something to say to you.
Right.
And so then you go through your loop, for I = 0 to 2. Do you have something to say to me? Yes, I'll deal with you. Do you have something to say to me? Yes, I'll deal with you. Because your select call told you who has something to say to you.
But his point is you're always starting with 0.
Yeah, but you're dealing with all of
You
them.
can't. I can see how you can do it. Once you're basically using the same read file descriptor set and process the entire thing first
Yeah.
before you go back and select again.
Yeah, that's how
Yeah.
I implemented it, and it was working
Yep.
fine.
Okay, that will work. Yep.
So we're assuming that clients aren't going to actually try to talk over each other, or we don't
Yes.
care what happens in that
Yes,
case?
that will happen. Yep. You will see garbled output,
If you don't
basically.
care?
Yep, that's fine. That is the behavior defined by the description of the homework assignment. Okay. Does everybody get that part about how you can do it fairly without any explicit use of a queuing method? Once you get a file descriptor set from the select on read on the server side, process all the bits first before you try to select on read again. So that's that's one way to do it.
Could that hang up the program though if one person never really? I guess it would anyway. Wouldn't it?
It wouldn't hang up anything unnecessarily. I mean, it would not have hung up something that you would otherwise be unblocked.
I'm kind of confused. You've got 3 clients sitting out there,
Uh-huh.
and you do a select, and your select is only going to return back on the server because one of those 3 clients had an input. But if we're just sitting there manually typing in an input, I can go to client 1 and type in A. My server program immediately returns from the select and immediately.
It does not. You have to press the enter key first if you're interacting on the.
I just can't.
Console.
Yeah, but if I press the A and I press enter,
Right.
and then the server picks it up.
Right.
I mean, it seems like it's going to pick it up and process it before I can go to another client screen and do anything anyway.
Yeah, but my test script is going to set up parallel threads or parallel processes, so that it is not truly interactive anymore. So it's not one person trying to work on 3 different terminals, because my test program is actually running 3 different processes in a script, so they can send stuff out at the same time
But as far as us,
simultaneously.
as far as us testing it, I don't see how we're going to see anything different no matter what we do.
That is correct, and that's why whether it is fair or not is okay. I mean, because you cannot easily test it. Yep. Okay. Are there any questions about this part? Okay. The 2 methods are you can do one single select on read, process all the file descriptors that are ready to read, and then go back to select on read again, or you can select process 1 and then go back and select again, process 1, go back and select again. So the first method is more effective, more cost effective, and it also ensures a certain degree of fairness. And then the second method is just easier conceptually, because you're just redoing things unnecessarily, but it does make the loop seem simpler, because you don't have to go through every single thing within the file descriptor set. Yep.
But in some scenarios, you would actually have less garbled output with the second scenario, because if the first client is talking, the first client's message is always going to get through, ungarbled. And if the first client isn't talking, the second client is, the second client's message is always going to get through. And if those 2 are quiet, the third one is, then it's going to get through. And the only time you get garbled messages is if one higher priority one interrupts a lower priority one.
Mm-hmm.
But I suppose we don't care still.
But that only makes sense. But that only makes sense when you're implementing some sort of protocol and you have a predefined pattern that needs to be transmitted without interleaving.
But see, I thought that we were kind of assuming that because we are using cooked input on our because
Standard
we're
in.
sending cooked input.
Because standard in is cooked.
Yeah, so I
But
thought
when my
that-
script runs it, it's not cooked anymore because it's not interactive.
Valid. Okay.
Yep. Okay, any other questions about this one? So for this homework assignment, you will have to open up multiple terminals in order to test the program. Does everybody know how to open up multiple terminals in your environment to test this program?
Just like we did last time, right?
Yeah, exactly. Yep. Okay, any other questions about this? The one about last time is a little bit special because that one doesn't really require interaction. So you could have redirected the output of each process to a file and then use the ampersand to run it in the background. So it doesn't truly require a terminal to be open, because you can just use the ampersand, run the server first, run the first client, run the second client, run the third client. When they're all done, you look at the captured files from standard out, and then you can see whether your program works correctly or not. Which also means that with the homework assignments that was due today, people could have integrated a test setup within the makefile. So you can say make test and make test a pseudo target, and you can check everything. Is that what you did?
Yeah. Of course, the first time I did it wrong, and it just looked terrible, and it looked like the program was haunted because they were all outputting to the same screen, character by character.
Yeah, but with this one, you can with the the assignment due today, you can redirect it because there's no interaction. But with the other one, with the other homework assignment, you cannot really redirect it easily. You can if you want to, because the server still has to wait for all clients to connect before it does its broadcasting job. So you would run the server first, run the first client with redirection, run the second client with redirection, run the third client with redirection, and then we'll just go like that, and then all three processes will be done in the nick of time. Then you can look at the output from each client to see whether it is actually seeing the broadcast from the other clients. If you want to test it that way, I would recommend client 1 to send just AAAA enter. Okay, client B 2222 enter. Client client 1 would do AAAA enter. Client 2 would do BBBB enter. Client 3 would do CCCC enter. So that way you can clearly see which character is coming from which client, and you have to make sure that all the numbers are accounted for. Okay. Any other questions about this homework assignment? No questions? All right. So this file is already saved. If anyone wants me to upload it, I can do that. And do you guys find that useful in the scenario diagram?
Sure.
All right. So what we're going to do is we'll skip the next one. Okay, we have actually socket 3 here, but we'll skip socket 3. And what we'll do is we'll go to section 4, and we'll talk about something else before we come back to socket 3. Because I think most people have enough of sockets for now. And you know what? All of these are still under file systems. What have you guys been dealing with over the past 4 weeks or so? File descriptors. And that means file descriptors, or the concept of files, is a very powerful one, because you can have inter-process communication only appearing as file operations, read and write. So what we'll do is we're going to move on to section 4 and talk a little bit about interrupts, system calls, and signals, particularly signals. So we'll go ahead and start with this one first. It's module 0216. Okay, this one is actually borrowed from one of my assembly programming classes, or at least the first part is. The second part is unique to this class. It talks about signals. But we don't want to talk about signals until we have talked about interrupts and system calls, or system services. How many people have some exposure to hardware interrupts, or why we have interrupts in hardware? About 2, 3. Okay, so I'll go ahead and explain what interrupts are, and then we'll proceed to talk about how it connects to system calls and how it connects to signals at the same time. In the some of you will find this boring because I used the same example in cisp453. But if you have forgotten what you learned from cisp453, this will be just as refreshing. So I can see from whether people are bored or not. You'll see whether they can still retain what they learned from cisp453. It should be boring by now.
Unless we didn't take it from you.
Right. Well, in other cisp453, they should talk about interrupts as well. At least the concept. It's really hard to actually play with it because we have protected kernels, but the concept should still be discussed. All right, so let's go. Let's do time travel, and we are now back to the late 70s and the early 80s. Okay, back in those days, personal computers are truly personal in a very personal way. I learned this from Kung Fu Panda. He was trying to describe himself in his dream, as the superhero. What was he trying to? What was he saying in his dream? It was Kung Fu Panda 1, and he was in the dream. He was the swordsman. He was trying to use the same word over and over again because his vocabulary was really limited. Anyway, when I remember, I'll talk about it. Okay. Anyway, so back in those days, personal computers are personal because they only have to handle one user. Okay, not like Unix. I mean, Linux can easily handle multiple users at the same time. Okay, even the live CD distribution, which is mostly people use it on a single computer, but because OpenSSH is already installed and running, they can accept multiple connections, and you can have multiple people logging in at the same time using the system at the same time. But DOS and CPM were not designed like that. They were designed for a particular user, using the computer at the computer. Yep.
I have to ask, what is CPM?
CPM stands for Control Program slash Master, I believe. These terms are really kind of old and cost per mile. No. Control program. Let me look for control. Yep, control program slash monitor. It's basically an operating system, but before the phrase operating system was coined. Okay, so that's a operating system, and it was a precursor to DOS. That was another interesting history in Microsoft history book. But anyway, back in those days, or if you want to connect to this, you can also imagine the early versions of DOS, DOS 2.0, DOS 3.0, and I think all the way up to Windows 98 or Windows Millennium still uses the same type of mechanism. Okay, so imagine you are the operating system. You only have to handle one user at a time, and the user is always at the terminal, okay, using the keyboard, and that's before the mouse was even used on computers. So this is the only device that you are going to use to interact with a user, and there's only one thing the user will do at any particular time. If a program is printing to the printer, the person will not be typing. Okay, there's no such thing as multitasking. Okay, you can only do one thing at a time. All right. So you're the operating system, and remember, you don't have hard drives either back in those days. You have slow floppy drives and so on and so forth.
Cassette tape. Cassette tape.
Cassette tape, and you don't have any audio input. There's no way to do screen recording. Like having a microphone and all kinds of devices connected at the same time. In other words, it's really boring. Life is boring from the operating system's perspective. This is what you need to look for for input. User input comes from here. So as a lazy programmer, what are you going to do? Well, you will use what we call a polling technique. In other words, you'll sit in a tight loop, and then you ask the keyboard controller and say, hey, keyboard controller, do you have a key event for me? When you press a key, it's a key event. When you release a key, it is a key event. In other words, from the keyboard controller's perspective, it doesn't give you like Control B when you type Control and a B. When you type Shift T, it doesn't give you uppercase T. It is like two separate events. The Shift key is pressed. The T key is pressed. When you release the keys, they will also generate the equivalent events. Okay, but when you're not doing anything with the keyboard, obviously there's no event. But the program keeps asking. Okay, that's how it finds out whether something is there to process. What is the problem with this approach?
You're always using 100% of your available processing power.
Yep, that's definitely one problem. If we are to use the same approach on the laptop computer, the battery life will drop down to
0.
well, pretty low. I mean, your computer will run warm and hot all the time. Okay, but back in those days, we don't have, they didn't have laptop computers. They had luggable computers, okay, which is basically a computer in a suitcase with a tiny little screen. So that was not the main concern. Okay. But later on, we have different type of things. So in those days, when you use WordStar to type a document, and you say, oh, I want to print it out, and it turns out to be a 50-page research paper, you cannot go back and say, okay, when it's printing this document, I'll go edit another document. There is no such thing, because when CPM or when WordStar talks to the printer, it uses the same approach. Okay, it will send all the dot information to your poor 9-pin dot matrix printer, which can only take so many dots at a time, right? So the printer will send back and say, stop. Okay, my buffer is full, don't talk to me anymore. And then the operating system will do what? It's going to stay in a tight loop and say, hey, printer, can I talk to you again? No. Hey, printer, can I talk to you again? No. And we keep doing that until the printer finally says, okay, give me another 16K of bitmaps. Okay, here is 16K of bitmaps. And then we would get back into the tight loop and ask again and again, okay? And that's back in the good old DOS days, okay? CPM and DOS are pretty much the same thing. And then Windows came, okay? What is the main difference between Windows and DOS? For those of you who know the products. Multitasking, okay? Windows kind of implies that you can do multiple things at the same time, because hey, I can have all these. I can have Word. I can have. This is before Internet Explorer was even there, so I can have Word. I can have Minesweeper and Paint. Okay, Paint has always been there since the beginning. So I have Paint, Minesweeper, and Word, on my Windows screen at the same time. I expect that I will be able to use these applications at the same time. Okay, if you have a game that has some timeout features, like a real-time game that needs to know how much time has passed, you expect that game to keep track of the progress of the game and the time and also the animation while you are doing something else. Okay, and for the most part they do, but not because of the operating system. It has to do with the applications being cooperative. Okay, so once again, I pick on the first 3 people in the class. So you guys will probably be sitting in the back next time. Okay, so let's say we have these 3 applications running in Windows 3.1. Okay, the first successful version of Windows. You guys have to play nice. In other words, when you're done doing a little bit of work, you have to say, oh, I think I've hogged enough time of the CPU already. It's your turn. Okay, so it's your turn, and then you will do a little bit of work, and then you look at your clock and go like, okay, I think I got enough time from the CPU already, and you have to move on and let the third application to get some processing time. And when you're done, you pass the ball, quote unquote, the ball back to you, and then just kind of go like this. It's called cooperative multitasking. Okay, as an operating system, Windows 3.1, I don't do a single thing. I just let you guys manage the whole everything. Okay. And then here comes DOS, okay, a DOS box in Windows, okay? You can open up a DOS box in Windows 3.1 and all versions of Windows, so that if you need to, you can use command line interface to type in commands. But DOS, remember, comes from CPM, and CPM says, I only have one thing to do. So you come along and then you say, I'm going to ask the keyboard controller for keyboard events. Indefinitely. So you're sitting here saying, hey, keyboard controller, got anything? No. Hey, keyboard controller, got anything? No. What do you think the other 3 applications are doing at that time? Absolutely nothing. You're hogging all the processing resources. There's nothing left for the other 3. Okay? So that shows you the limitations of this particular approach. Okay, if you're doing polling, you can do it when you have a single user, single application, non-multitasking type of environment. In Windows, it is still single user, but now you have multiple things that can go on at the same time. that approach doesn't work anymore.
And in this age of viruses and malware, I can't even imagine how bad it would be if you let programs determine how much CPU time they were going to
Yeah.
get.
I was thinking the same thing.
Yep.
Imagine
well,
what you could do
you know,
with 100% of the CPU time.
From the operating system perspective, that's actually the least of your worry. Because in Windows 3.1, which has absolutely no protection across applications or the operating system itself, everybody, the operating system, the 3 applications, all your device drivers and whatnot, they all share the same memory space. Everybody gets to see everybody else's stuff. And modify too. It's not just seeing, it's modifying too. So that means if Word decides to misbehave for any reason, it takes the whole system down.
Well, that's your virus protection. You get the blue screen of death every 5 minutes, so.
Yeah. Yeah, the virus has no chance of acting, right? Actually doing anything. Yep. There's no protection. The operating system, which is the most important part of the entire thing, cannot protect its own memory space from the applications. If an application decides, I want to overwrite location 0 with this content, hey, it's all yours, no problem.
Awesome.
Yep. But that's a different story for another time. But right now we're just kind of focused on the resource hogging of DOS. Okay, because DOS is the DOS box is hogging all the resources because all it does is to keep asking the keyboard controller for an event when most of the time there's nothing, right? So that's why we have the concept of an interrupt. Now, to be fair, Intel and also all the other processor manufacturers actually had interrupts implemented on the processor. And the motherboards also support interrupts from the very beginning. It's just that the whoever wrote CPM decided not to use that feature because there was no need to make the program any more complicated than it had to be. Okay, and Microsoft got a clone of CPM and resold it to IBM as PC DOS. Well, also changing the copyright notice and stuff like that, but for the most part, it's a clone of CPM. They did not rewrite it for anything, and in the DOS days, there's no need to rewrite it either because it's still single user and single application all the time. But when they move on to Windows 3.1, which is the first successful version of Windows, people start to demand and say that, hey, how come my Windows environment is not doing anything anymore? Once I start up a DOS box, it doesn't do anything anymore. Okay, so now you have to actually make use of the hardware feature called an interrupt, or called the interrupt feature. Now, in order for that to happen, you need support from not only the operating system, but your hardware actually has to support interrupts as a concept first. Okay. So that's basically, section 2 talks about life without interrupts, which kind of sucks, without, interrupts when you have a multi-application and multitasking type of environment. So when we talk about interrupts, it requires support from 2 sides. It requires support from the processor side, which means as a processor, I have one pin. Okay, as a processor, I have at least one pin dedicated as the interrupt pin. Okay, this is from the hardware perspective. If this pin sees, now this part can be a little bit confusing because what they usually do is they invert the logic on the interrupt pin, which means when the interrupt pin has a high voltage, it means everything is good, there's no interrupt. When the interrupt pin has a low voltage, that means there is an interrupt and the processor has something to pay attention to. Okay, the reason why it is quote unquote inverted like that has to do with pull-up resistors, and in the early days, this is an easier way in order for multiple devices to share the same interrupt pin, which is fine. Okay. So imagine your interrupt pin as the bell on a bus. Okay, or in the good old days, you actually pull a line in order to tell the bus driver that you want to stop in the next stop, right? So that's your interrupt pin. Okay. The driver on the bus is the processor. So the driver has to pay attention to the line, the bell that says somebody wants to get off at the next stop. So that's why you need support from the processor. The device, which is you as a passenger, is the one that is quote unquote generating the interrupt. Okay, so for the most part, when you're riding a bus, you don't want to bother the driver, right? You don't want to chit chat with the driver, because it can be dangerous if the driver is distracted. So for the most part, as a passenger, you stay quiet, you do your own thing as an I/O device. You may be writing to the hard drive, reading from the hard drive, waiting for something to happen on the NIC, network interface card, waiting for any keyboard event, waiting for the mouse to be moved, okay, so it can report a new location, and so on and so forth. So for the most part, the passengers are quiet on the bus. But occasionally, you have something to tell the bus driver, okay? You see a keyboard event. Somebody press a key. So somebody has to process that. The device itself doesn't know what to do because it doesn't, it's not its job to interpret, the key presses. Okay. So as a passenger, the keyboard controller would yank the line and say, "Hey, driver, I need to do something." Okay. But the driver cannot really do anything like right away. Okay. The driver has to finish up, the last operation that cannot be interrupted, that has to be atomic. Okay? This means when you're executing instructions at the lowest level, interrupts can only happen between the execution of instructions. It can never interrupt in the middle of the execution of an instruction. Okay? If you remember from cisp453, the assembly programming class, it doesn't matter from where you take that class from, but in that class, you specify individual low-level instructions. Each instruction, or most instructions, are called atomic because the instruction itself cannot be interrupted. But between the execution of instructions, the driver can say, "Okay, let me check. Oh, the bell line has been rung, so I should pay attention to whoever is yanking that line." Okay. So what happens in that case is it's called interrupt handling, okay? Because you have a device, calling for the attention of the processor. The processor finishes, an atomic operation, is ready to handle the interrupt. So the processor will look at the interrupt line and go like, "Oh, okay, something requires my attention." This is all done in hardware, by the way. It's not done in software. So none of this is under software control until when I say it is under software control. So the processor will first, say, "Okay, who needs my attention?" Depending on the implementation of the processor, you can have one interrupt line per device. You can have multiple devices sharing one single interrupt line. But let's say you have multiple interrupt lines, which is more common with modern processors. So the processor will look at, okay, I have 6 or 8 interrupt lines, 1, 2, 3, 4, 5, 6, 7, 8. Then it will say, "Oh, okay, it is the 7th device that requires my attention." So at that time, the processor will first remember what operation is interrupted. In other words, exactly where in memory it is executing at this point. It will push that address on the stack so that it knows where to go back to when it's done with handling this interrupt. Now this is all done in hardware, okay? It's not under your software control. This is all automatic once you set up the system. So we'll save all the information that it needs in order to restore back to that point of operation. And then what it will do is it will look at the interrupt lines and say, "Oh, it's the 7th interrupt line that requires my attention." It has a lookup table. It's called a vector table. And in the table it says, okay, if you see someone requiring your attention at interrupt line 1, go to this location. For interrupt line 2, go to this location. If it's interrupt line 3, go to this location. So each source of interrupt has its own location in memory to specify the code to handle it. Okay? So it will look at this table and then find out, okay, this is where I need to go in order to do something in software to handle that particular hardware event. So the execution will then continue at what we call the interrupt surface routine, ISR. Okay? The ISR is written like just about any other program that you write. Okay? You can even write it in C in many cases. Okay? But it does have to interact with the hardware. Because if you don't remove the keyboard event from the keyboard controller, it will keep the interrupt line held because it is not handled. So the first thing you want to do is to remove the event. You stick it into a buffer of some kind. You notify the operating system and say, okay, there's a keyboard event available for you to process, and then the ISR, its job is done. Okay, just like a subroutine that you usually write, a function in C that you write. When you're done with an ISR, it quote unquote returns. Okay, but when it returns back to whatever the interrupted to begin with. So the interrupted code does not even know that it had been interrupted. Are we doing okay so far with that concept? Yep.
So what if there isn't anything executing? Like if
good question. Okay, there's no such thing as nothing to execute. Okay, if you have absolutely nothing to execute in a modern operating system, what happens is the OS, the operating system, is actually quote unquote stuck in a loop, but it's not quote unquote a tight loop because it's a loop that involves either the sleep or the halt instruction. The sleep or the halt instruction has a special property. When it does execute, it puts the majority of the processor to sleep in a suspended mode. Okay, so that means the transistors are not going like that. They just basically stay static for the most part. When an interrupt happens, it wakes up the processor from the halt or the sleep instruction. So it will go and do whatever the ISR needs to do. When it returns, it's returning back to the loop. So the loop will go for another iteration, but it will encounter the same sleep or halt instruction again, and then it goes back to sleep, which is low power consumption. So that's basically what when the system has absolutely nothing to do and only has to process interrupts. That's basically what's happening, and that's why with modern operating systems, they don't consume as much power because if there's nothing to do, they would execute this kind of instruction, which puts the majority of the electronics of the processor into a either slower or completely stopped state, which does not consume electricity. That was a very good question. Okay, so we still haven't really gotten to the part of privileges. Okay, and that is the other part about what we just talked about. Remember, we talked about how Windows 3.1 will not protect the operating system from everybody else. That is what Section 4 is about. So we'll continue this discussion on Monday. And you guys have a... No, wait, today is Monday. We'll continue this on Wednesday. And then hopefully we'll get to signals on Wednesday. Then we can actually start to do some programming. Yep.
If you want to see the dream from Kung Fu Panda, it's Dream of Kung Fu Panda from 22.
He was trying to describe himself as a
Something about awesomeness or something like that.
legendary. That's it.
Yes.
Yeah, this is the legendary stuff that's made out of legend, and he just kept using the same word over and over again. All right. So I'll see you guys on Wednesday. Start on the homework assignment. Okay, you have everything that you need to start on the homework assignment. The structuring of the program is the most important part. So you got to have to design the program before you start coding it.
I'm gonna run home and email that to you.
Okay.
Also, on the first assignment, I didn't. Well, I had it done, but